Let's look at another problem in the moment of forces and coupled moment and equivalent system. Gear C is rigidly attached to arm AB. Okay, so that means when forces are applied to the arm, it's not just going to freely rotate. It creates a moment. They move together. Gear C and arm AB are moving together. That's what it means. If the forces and couple shown can be reduced to a single equivalent force at A, determine the equivalent force and the magnitude of the couple M. All right. So when you're reducing a system or moving forces around, we have two main governing equations. The equivalent force is always summation of the forces, and then equivalent moment is summation of all existing couples moment plus summation of all R cross F's. Why? Because once you move forces around, once you mess with them, they're going to create a moment. If you move this last force, take it from point B, put it at point A, it will create some moments. And the way we keep track of it is by R cross F, or in this case, we can do FD, or we can do combination of Cartesian vectors and scalar notation, because moving forces around. This is super simplified. Again, there's a lecture on this that you can watch that I put online, but this is the governing equation that we're going to use. I'm going to rewrite them here. For the moment in this case, I know we see R cross F. It's a 2D problem. We can get by with using Cartesian notation, but then we still got to keep track of all the pluses and minuses. So there is one existing couples moment, so there's just M, and we usually go this way positive, so that one is positive, minus then all of the summation of all FDs, and that D is perpendicular distance between point A and line of action of each force. So that's perpendicular distance. So we have to do, what we have to do is M, that existing M, minus F1 D1 minus F2 D2 minus F3 D3. But the problem is kind of telling us when we do this, we're going to have just a single equivalent force. So this resultant moment is going to be 0. Okay? So there won't be any moment. In other words, whatever those three forces are creating about point A is going to be equal to this existing couples moment. As a result, we're going to have no moment, just an equivalent force there. So in other words, we can calculate that moment, and it's just going to be summation of those forces, three forces and their distances. So sum of all, or sum of moments of all, moments of all forces about A. Okay, let's just start with this one, with equivalent forces. Then we'll get back to this for the second part, because it needs to calculate that that M. I'm going to use Cartesian notation for the forces. Let me draw. Let's take this as beam AB. Then I have one force right there. stop drawing. There. 30. I have another one that's straight down. 40. And then I have another one right here. So it's a little bit of a trig work that we have to do to figure out the angles and all that. But this is going to be my x-axis. This is going to be my y-axis. All I'm trying to do is find FR, summation of each f. So let's write it as Cartesian vectors if we can. So x component would be right there, and this one is 18 sine 30. This one right here is 18 cosine 30. The 40 is just a straight up and down. This one right here is 25 sine 40. And this one is 25 cosine 40. All right, I have everything in x and y. I'm going to write it and just add them together. So all I have is minus 18 sine 30, because it goes against x-axis, and that's I, minus 18 cosine 30, that is j. 40 is a straight down, minus 40j, plus 25 cosine 40, that will be I, minus 25 sine 40, and that will be j. Some people might like to just do summation of x's. Some people might like to do summation of y. That is totally fine, and you can do that. I figured this way it's much easier. So my FR is going to be 10.15 I. Sorry, this one I didn't put any units anywhere. All of them are units of pounds. Minus 71.65, and that's J, units of pound. So that's your single equivalent force. If you want to do magnitude and angle and direction, all that, we can absolutely do that too. Just take it one further step. You all know how to do magnitudes by now. And that will result in 72.4 pounds magnitude. If you want to do angle, if we look at this in x and y, x, y, I have 10. So it's a 10, 1.5 pounds on x. And then I have minus 71, 6.5 on y. So the angle of this FR, this is this FR. Whichever angle you want to take. I'm going to take this one as alpha. Tangent of alpha is going to be 71.65 over 10.15 pound. They get canceled, and you should get alpha about 82 degrees. So if you want to express it this way, it's totally fine. Or magnitude and angle, that is absolutely fine too. So please pause here, spend as much time as you want, and look on the angles and work your way through this. But now we're going to go back to this part, the moment part, and find that moment FD. So I'm going to take a little bit of a different approach here, because that FD, this D should be perpendicular distance of A and line of action of each force. So for example, this force, this is its line of action. you have to find this distance. This is your D1. This force here, you have to find this distance. That's your D1, perpendicular distance. And this one, line of action is like that. You probably have to go here. This is the perpendicular distance, and that is your D3. So it will be a little bit of a challenge in trig work and finding all that. So instead, what I'm going to do is I'm going to resolve each of these forces into a perpendicular component to the beam and a parallel one, perpendicular and a parallel one, perpendicular and a parallel one. The good thing about that is all of these parallel ones, they go through point A, so they're not going to create any moment for me. And these ones, sorry, the figure is getting a little bit crazy. These ones that I have, the perpendicular ones, the perpendicular distance between point and line of action is all given here. 22 inches to this one, 22 plus 10 to the second one, and so on. So let's resolve each force into a component that is perpendicular to the rod A, B. It's just a little bit of a trig work, nothing that you can't do. So this angle here is 30. So in order to go perpendicular, we go parallel to the rod. This will be the perpendicular component. We go perpendicular, and this will be the other component. We're not really interested in that one. We're only interested in this one. We just got to find the angle. So this is vertical, perpendicular to the beam. The beam has an angle of 25. It's given. So that means this is 25. So that means this whole thing is 55. So F1 or let me write it here. This component is 18 cosine of 55 degrees. The distance for it between line of action of this force and point A is given to be 22 inches. So let me write summation of FDs. Let me write it. So it's going to be 18 cosine of 55 multiplied by 22 inches. Let's keep track of the rotation of it too. It's going this way. Next, we have the 40. The 40, this one right here is 25 degrees because the beam has a 25, or the rod has a 25 degrees. So perpendicular line would make it 25 degrees as well. We're only interested in this component right here, and that will be 40 cosine 25. So 40 cosine 25. The perpendicular distance, I feel like I should clean up this here a little bit. There. Perpendicular distance between point A and this right here is 22 plus 10. Okay, rotation, keep track of it. Okay, and the last one is right here. We have this angle here is 40. So this is 40. This is 25, same as this angle. So that's 65. This whole thing is 65 degrees. So then perpendicular component, if I wanted to keep track of it, is 25 pound, and that will be sine of 65. So 25 sine 65 Perpendicular distance, we're looking right here. That's the line of action. This is the perpendicular distance. So we're looking at 22 plus 10 plus 16 inches. Keep track of rotation of it this way. If you do the math, you should get 2474.8 pound inch. If that number is a little bit large, you want to express it in a different unit, you can divide this by 12 and you will get a little bit of better number to express that, and that will be pound foot. So this moment here, that's the magnitude of that moment that we found. Again, please pause it. I apologize, the figure is a little bit messy. Another thing that I would like to mention here, you can go 18 sine 35, results in the same answer. And for this one, you can go also 25 cosine of 35, or 65 minus 9, 25. So this is also same, you should get the same answer. Thank you very much.